All right, so amides, the missing video. We'll see if it records this time. It's good you're all here, so in case it doesn't. The thing is, this is an amide. I'm going to start with the naming part down here. Is you're going to have the nitrogen. That's why it's always taught with amines. It's going to be a nitrogen attached directly to the carbon with the double bonded O. And so that carbon with the double bonded oxygen is always going to get the number 1. And so this one's just really simple. It's propane because it's 3 carbons. And then we drop the E and just say amide because that's it. This one, there's 2 carbons, so that would be ethane and then amide. And then because these are side groups, when the side group is on a carbon, the carbon has numbers, but when it's on the nitrogen, you have to give them each an N because both of these, so NN dimethyl ethanamide. And so that's how most of you are going to name it. I've noticed that there is an alternative name. Instead of ethane, you can say acetamide. So acetyl is for 2 carbons. Either way is accepted. The acetyl, like acetic acid, is 2 carbons. The first carbon is that double bonded oxygen one. And it's just the common way that most people actually use. And this is benzene. And again, it has that extra carbon, so it is benz. And so it's benzamide. So pretty simple for those for naming. So drawing them, you're going to start at that ending there. And so prop, you can do it with zigzags if you like. And I'm going to draw these backwards to how I was drawing everything because carboxylic acids are just traditionally, but that's 3 for propyl. And then on that number 1 is the nitrogen. And then this is telling us the isobutyl is on the nitrogen. So in isobutyl, we have a kink and then the peace sign. So that's an isobutyl. Now, you always show the nitrogen, like oxygen. You always have to write the letter in. You have to show that it has 3 bonds. So you have to write in any hydrogens. Even when you do the zigzag on oxygens and nitrogens, you always have to actually write in the letter H. And again, up here, I just realized there's a picture. And so these can be H's or they can be groups and they can be anything. So we start at the end, butyl. And you can draw it either direction. So if you want to draw it here, 1, 2, 3, 4, right? There's my 1, 2, 3, 4 for butyl, the nitrogen. And then the 3 is saying at carbon number 3, we'd have our methyl. And then on the end, you have an ethyl. There doesn't have to be anything on the end. You can have up to 2 groups. And then we show a hydrogen. So the nitrogen, you don't show the dots on the nitrogen, but nitrogens make 3 bonds. In the amides, they never make a 4th bond. That was something in the amines. There's an ant. Did you guys see that? So whenever you see an ant, you've heard me say this, like we can name it Auntie Anne. That means there's not going to be an earthquake for at least a week. So the ants disappear when the earth starts. Apparently, we're the only ones insensitive to this. So whenever I see an ant, I used to like freak out. I'm not going to kill it because that's the Buddhist nature, right? That you don't ever do that. But all right. So benz is you can either show like this one or make sure you show your ring, either one or the other. You have that 1 carbon group with the oxygen and then the nitrogen. And then the nitrogen has an isopropyl. And these are alphabetical, so that's why the N group came second, because the isopropyl starts with an I. And then the P means para, which means it's at carbon number 4 in the benzene. And that would be an ethyl group, which is 2 carbons. And so that's my para-ethyl. And so these are pretty cool. These are extremely common because where we're going to see amides in our body, the big place you find them is proteins. That's why they're called peptide bonds. And so a lot of people say amides I say amides. I say it both way, amides. And all right, I'm gonna keep going. If you guys have questions, boiling points, they do H bond. So these are gonna be in the second highest group. Remember, our highest group are ionic. These are not ionic, but they do have, oh, you know what? It's a good thing I went back up here. You do have to draw the hydrogen on the nitrogen. When I have other things, I like to draw it either above or below, but you do want to make sure nitrogen has 3. But all of my nitrogens had at least 1 hydrogen. And so that H bonding means these are going to be in that category with the alcohols and amines and carboxylic acids. And solubility. So again, it's these guys will be, they do like water, they love water, as long as there's not too many carbons. And so we're talking total number of carbons. This one would probably be slightly water soluble because there's 7 total carbons, but there is a point, like this one is doubtful, it would be water soluble because you have too many carbons, even though we have a nitrogen and oxygen. So the smaller ones will be water soluble, but as we start adding more and more. And so the general rule, and it's not a very good rule, is maybe 6-ish. Amino acids, I don't know if I talked about this with the amines, they're actually in the ionic form when they're in our body. And so ionic are always going to be water soluble, but these are not going to make ions because they're not an amine. That double bonded oxygen doesn't allow that. And so this is the key property here, is they are neutral. And why this is important is we're going to see on the next page, they are made from carboxylic acids, which are acids, and amines, which are bases. So you take an acid and a base, and when we put them together, you lose the acid and the base. These guys have this means neutral as far as pH. So they have absolutely no effect on pH. All right. And yeah, I was gonna say, well, the recent guy's drinking coffee, but coffee has amine groups in it, and so this is a picture of a protein, and so if you get to take Chem 106, which would be wonderful for me, but I don't think any of you need it. But if anybody does in the future who's watching this, we get to talk a lot more about proteins, and they're just these beautiful, elegant, and something I talked about in my nutrition class yesterday. We talked about vibrations and just something to put out there because we've all heard about proteins. We learn about them and we get really geeky about the DNA makes the proteins. The one piece that nobody understands is how the protein knows to go into this beautiful structure. And when you look at this with these beautiful alpha helices, this is definitely a vibrational structure. And so I'm going to put that out there because we get so caught up. I mean, I have you do these papers and all about the molecules and naming them, and we get really into it and we start getting pretty good at it, and the isomers. But really, they're made up of atoms, and atoms are 99.9999999% nothing. They're vibrations in the nothing. So they're actually, we are more vibrations than we are the material world that we're so focused on. And proteins show that so beautifully. What shows it even more beautifully is DNA. DNA is like the perfect harmonic. And so if you've never looked, you know what DNA looks like. It's a vibration, right? It's that double helix. And you don't have to be a music major to say, oh my gosh, it is. It's like a perfect harmonic. And ours is gorgeous. And so we're going to see peptide bonds. There's my little friend, Auntie Anne, we'll call it. A peptide bond is an amide, and we're going to go through this on the next page. And so that's what's the bond between amino acids. So if you have an amino acid, we have a carbon with 4 groups around it and another carbon. And so one side is going to be an amino group and the other side is an acid group. It's up to you if you want to draw this. And an amino acid, always the R group is just that it's something different. But an amide is that we're going to see a link happen. We pull out the water. So we lose the water, and So the OH on the acid and the H, you still have one H on the nitrogen, and there's our protein linkage, which is that. Our body, like when we eat food, we have to actually cut these, which is hydrolysis. And that's going to happen in our stomach, especially. But the big thing with proteins is you first have to unravel them. And we can only absorb when they're single amino acids. And that's one of the issues we have right now is we're changing proteins, and our body wasn't designed to cut these proteins because our enzymes can only cut at certain amino acid sequences, and those are all naturally found. And so gluten has been changed, and that's why so many people have gluten issues. Casein, which is in cheese, most everyone has issues with casein and digesting it correctly because we can't digest the amino acids in the sequence they're in. All right. So the reactions are pretty simple. As I just went through, if you take a carboxylic acid and amine, you get an amide. You always need some kind of catalyst or an enzyme, to have that work. And so in our body, there is an enzyme which is going to hook them together. And this is going to happen in our body when we make proteins. This happens in the ribosome. And so, and it requires energy to do it. But if we draw our benzoic acid, which is, right, that's our benzoic acid. And then when you draw the amine, it can be really nice to draw it. And I'll draw the CH3 on there, or maybe I should draw it in a different color so you could see. And you could have just shown that as a line too, but here is, this is that cowgirl chemistry that you find the water molecule. So like when we did esters, it's a similar idea. You're going to lose water molecules, so you're always going to get plus water. And I find some students like to write the plus water, and you're left then, our product, we have the benzene with its double bonded oxygen, and it's going to hook right into the nitrogen. And the nitrogen's still going to have its CH3. You could just show that as a line and a hydrogen, or you can write the CH3 in. That's kind of up to you. The name would be N-methyl, and then benzamide would be the product. Now we do our second one, propanoic acid. So 3 carbon acid, right? So 1, 2, 3, and our diethylamine. So you have only 1 hydrogen because you're going to have 2 ethyl groups. You can draw them with the carbons like it did above, or just like that. And there's the water molecule that you're going to lose. And so when we draw it out, our nitrogen no longer has a hydrogen on it. It's going to be connected straight to the propyl part. So the name for this would be NN-diethyl. I have you guys write the names because I think, one, if you write something incorrectly, which is easy to do on Zoom or even in person, when you look at the name, you can realize. And some people learn even better with the words than the pictures. And then propanamide. The AN is important because it's telling us this was all single bonds. And so that's the one direction. And then this is how we build and put it together. And then the opposite is called hydrolysis. And hydrolysis is what happens in our digestive tract. Amides specifically are in proteins. And so this is happening in our stomach because of the low pH. And so it's just going to break it into the carboxylic acid and the amino group, or the amine. And so I think it's really nice to show your slash, and it's going to be between the carbon double bonded oxygen and the nitrogen. And then you can just write, you don't have to, this is going to say that we have CH3. The carbons do not change at all. And so I think it's easier to just show it. And we're going to pick up an OH on this side. And on the other side, plus, you're going to have a hydrogen on your nitrogen. And the nitrogen had 2 methyl groups on it. And I didn't do that right. But that would be the water molecule, is what I was underlining there. All right. Some people can see what the answer is without having to draw it, which is, but we're going to draw our benzene and our nitrogen, and then there's an isopropyl on that, and there'll be 1 hydrogen. And then we can do the cut. And this one, we just have to be careful. So I'm going to do the cut, and then I'm going to go back and do the acidification step. So we're going to get benzoic acid. And so this OH is our new OH. And so initially, so this is still going to have the isopropyl. And what's going to happen is it picks up an H. It picked up a new H from the water that we added. But from this HCl, it's going to pick up 1 more H. And so it becomes, and it has a positive, and so the chloride's going to be attracted. So it's going to be an isopropyl ammonium chloride. And benzoic acid was our acid. So what I'll tell you, we're going to do one now, almost the same thing with the NaOH, is go ahead and do your cutting, and then the acid just means you're going to add an extra hydrogen to the nitrogen. And then this one, we draw our butane. So 4 carbons, right? 1, 2, 3, 4. The nitrogen is going to have an ethyl and a hydrogen, and we cut. So I'm going to count to 10 slowly while you all try that. So cut it into 2 pieces. The hardest part for me on Zoom, because nobody slows me down when I'm teaching it. So it's good. I can see you all. So the acid, this time the amino group just gets its hydrogen. So it's just ethylamine. And it's the acid that's going to change by the NaOH. So you're going to lose the hydrogen and the sodium's going to go on there. And so this would be called, sorry, we say the sodium first because it's the cation. So the cation always goes first. Up here, the ammonium name went first, and then the chloride goes at the end. So here's sodium, and then that's just butanoate. So just, our next class is a review class. I'm sorry, next Tuesday is a review day for us. So we'll see that we'll get to do a review of all this. And now I'm pondering if the review video was there. I'm hoping it was. Otherwise, we'll make it. I'm going to also back up because there was questions last time when I did something like this with the parentheses. I'm not a fan of the parentheses, but this is saying, 1, this hydrogen is incorrect. It can't have, that carbon could only have 1 hydrogen. It's saying both of these CH3s are on that. And so this was 1, 2, 3. One of those CH3s would be part of the longest chain. So it was a butanoic acid also up here on question number 3, and then there'd be a 3-methyl. So both those CH3s, or one of them you can cross off and actually show it attached there. Just because somebody will always ask me what would have been the name of that, and it is that one of these methyls is attached here at carbon number 3. So it's a 3-methyl butanoic acid. So when the carbon's attached, a methyl group's attached to the carbons, they get a number. When they're attached to the nitrogen, it just gets the N. Questions on the reactions? They're pretty simple. And they're really similar to the esters. It's just, all right. And this is also good practice if you haven't done the amine study set and worksheet. That kind of gives you a preview, but we're going to go ahead. I'm going to move on to the last.
Sherpa, could you
Yeah,
move back to the last page you showed? I kind of missed a little bit the writing the notes of that. Sorry. Methyl butanoic acid. Okay, thank you.
we good?
Yep, got it.
So for all the people in the video, I'm really sorry, but I'm thinking his voice was extremely loud because it kind of blew me away, and I don't know why that happens. So you guys ask the question, you might want to talk quieter because for some reason Zoom makes it like amplifies you. All right, so the practice page. So if you're watching the video at home, these guys, it's getting late at night because we just class presentations. I would tell you to stop the video and actually try this page and then watch the video and see how you did. Do you guys want me to stop? I can pause. All right, so we all just paused and tried it. Good job. We're going to see how you did. And these practice, so there used to be quizzes back in the good old days before COVID. And so we would do these practices before the quiz. This is quite a lot of practice. So this is also good practice for your celebration. So we start at the ending. So we're going to do 4 carbons. And again, it doesn't matter which side you show it. I like to have the double bonded O up, and it's an amide, so then that's connected straight to the nitrogen. And you don't have to number. I do that just to make sure everybody sees 1, 2, 3, 4. And then at number 2, we have a methyl. So that's my piece going down. And on the nitrogen, we have an ethyl. And so these were written alphabetically. E comes first, so that's why that's shown. And then the nitrogen, you do have to show its hydrogen. Again, nitrogen's going to have 3 bonds. All right, on this one, it's ammonium, so that means the nitrogen has 4 bonds. And not to the chloride, so we're going to save that. So you're going to do an ethyl. It doesn't matter which direction you do which in. You're going to do an isobutyl. So an isobutyl is the kink. It's like the elbow with the peace sign. So that's my isobutyl. And then you're going to have a pentyl, which is just 5 in a row. So that would be 1, 2, 3, 4, 5. So the nitrogen doesn't count. It's how many carbons. And so that's my pentyl. And then this would be my hydrogen. And so we want to write the hydrogen. And again, you can show them in any direction you want. It's just there's going to be 4 things. So you can have up to 4 different nitrogen groups. This would be called a tertiary because there's 3 different nitrogen groups. And then you technically would show a bracket. And this whole thing is positive, or you probably saw me do the positive on the nitrogen sometimes. It's up to you. You can show the positive on the nitrogen or outside the bracket. But the key point here, and why I'm showing it this way, is the chlorine is not chlorine, it's chloride. It's not a chloro. Chloro would mean it was attached to one of the carbons. It's chloride, which is saying it's an ion attached. It's not attached, it's attracted. It's our anion, to be more specific, right? And so it's attracted to the ammonium. This whole thing was our cation, our positive ion. And so this is the ones that are the highest boiling point. They're infinitely soluble. They're really stable. And again, most drugs are going to be in the ionic form. Nitrogens are really good for drugs. All right. We're going to name, and actually one of the things is we're also going to identify, this is a tertiary. So my nitrogen here in the middle has 3 groups. They could be all the same. In this case, they are different. And so I'm going to name them up here first because we need to alphabetize. So on the left, this is a methyl. So I'm just put an M. Above, 3 in a row, this is propyl. If it was attached in the middle, it'd be isopropyl, but it's just 3, 1, 2, 3. And then this is not a regular butyl because we're attached 1, 2, 3, 4. So it is a sec butyl, but sec butyl does start with a B. So alphabetically, it comes first. So there are different ways you can name this, but we're going to go with the amines just the common way where we just alphabetize the groups. So sec-butyl, methyl, there is a space in between propyl when you do it the common way, propylamine. There is an IUPAC way, and I'm going to show you that also. But the IUPAC way is going to be similar like the amides. And then that would be the 1, 2, 3, 4. We would call it a 2-butane amine. You don't have to do it this way, but we're saying the amine is on the second carbon of the butane. And then these become side groups, and they have to get the letter N. So this is the IUPAC way where we'd say N-methyl. I like the common way. It's like we did with the ethers where you just name what's around it. N-methyl, N-propyl. And then you tell me the amino group is on carbon number 2. And then it's called an amine. All right. This is an amide. And so that's carbon 1. You cannot cross the carbon, and it has a typo, so we're going to fix it. So I'm missing my hydrogen there. So I'll do it in purple so you can't tell I fixed it. So that is 1, 2, 3, 4, 5. So carbon 1, 2, 3, 4, 5. So it's pentane. We drop the E and we put on amide. And this is an ethyl group and this is a methyl group. So the ethyl goes first and it's on the nitrogen. So N-ethyl. And then the methyl is on carbon 2. So 2-methyl pentanamide. Pretty funky, but once you see it, it's like, oh, okay. And again, this here makes it the amide group, but that carbon gets to be carbon number 1. And then this last one, this is aniline. Aniline. I guess sweet aniline. And so that is when the nitrogen is directly attached to the benzene. If it's in the benzene, it's a pyridine or peroxine or something like, it's probably pyridine or purine. I always get those two mixed up. And that's an isopropyl. And you do have to tell me it's on the nitrogen. So N-isopropyl aniline, because this is then the IUPAC way of naming it. And this is the secondary, because the nitrogen has 2 things attached. They could be 2 of the same or 2 different. Making sure everybody's good. Any questions? All right, we're almost done. We can do reactions, and we either put stuff together or take them apart. And again, on the worksheet for the amines, there is a reaction that I probably kind of did, but not really. And so try it and then just come early or stay after and we'll look at it like always. So this is cutting. We're going to do hydrolysis plus water. So put your slash and then we just draw the two sides. And you could draw it with the carbons or you could draw it zigzags. So we can do it like that, or we can do our zigzags if I'm going to do it right. So it's a butanoic acid. Butanoic acid is the IUPAC way of naming it. It is commonly called butyric acid, which you may see in some of it. And then the other half is the nitrogen is going to have, it picked up a hydrogen. It's actually going to pick up for another hydrogen from the HCl. And then that is actually an isopropyl. So this group here is saying it's a CH with 2, that's isopropyl. And this will now have the positive and the Cl will be attracted. So this would be isopropyl ammonium chloride. And you can show it like that, or you could put, I prefer to write my hydrogens on the other side of my nitrogen. It probably has to do with being a biochemist, and the nitrogens are usually reacting and becoming something. So, but you could have also shown it like this. The key is the chloride is not attached, it's attracted. So it is ionic. And then the second one is acetic acid is just a 2-carbon acid. So again, acetic is 2-carbon and ethyl is 2-carbon. And I just think it's really nice to draw it so you can see the water molecules. So there's the ethylamine. And you can lasso your water molecule and kiss it goodbye. The water molecule leaves. So these are reactions going on in our body. It's really simple. We're just using water to come and go. And so you'll have 2 carbons on each side. The nitrogen's in the middle, and there's just 1 hydrogen on the nitrogen. So we would now say N-ethyl. And then if you guys said acetamide, I would not mark it wrong, but it would be called acetamide, would be a more common way of calling it. But again, that's 2 carbons. At this point, though, you have to tell me the ethyls on the nitrogen also. All right. And then the last question is really important. We're going to distinguish these with a simple test. And so if there is, one of the keys here is this is a tertiary amine because it has 3 methyls, and this is a secondary. And so amines, by the way, versus anything else are going to stink. They smell like rotten fish. And because that's what you're smelling is the amino acids. I don't know if I talked about it. I think it was in the extra video you could watch. The 2 worst smelling things, when they put them in something, the smell test, are carboxylic acids and amines. And you take the 2 smelliest things, a carboxylic acid and amine, really they stink to high heaven, and you make an amide, and the amide doesn't have a smell. Which is kind of hard to believe because everything else stinks. There's a couple different things you can do. They're both amines, but the tertiary has no H bond. And so that means if you did boiling point, the methylamine would have a higher boiling point because it has the H bonds. And I'm tired like you guys too. That's my best guess for that one. Solubility, they would be too close to really be able to tell. That's a tough test to do. On this one, though, they'd both be water soluble. This is ionic. And so one is going to be a solid form. There's going to be no smell. Whereas this is it's going to stink like rotten fish. And so you're going to know, you won't even have to smell the test tube. You're going to know. A warning, when you guys do the unknown lab this week, you're going to smell it to see, but the smell is a hard distinguishing test because several things have kind of a fruity, they all kind of have a fruity smell, and they're going to make you kind of, but the other test you could do is the higher boiling point is the ionic. Ionic is going to win like beyond anything. They would both be water soluble, so we won't do that. And then the last one, I would just do smell again. That the aniline would have the rotten smell. And also the other quick test you could do, sorry, I just realized that, is the amine is basic. So if neither of them, if you couldn't distinguish with smell, the amine is basic. Aniline is basic, which means the pH is higher. It would turn litmus blue. Benzamide is neutral pH. So again, smell is a tough thing unless it's really distinguishing. And so pH, I knew there was another simple test. So again, up here, the amine is a pH, is a base. That means it's above 7, or it would turn litmus blue. And as soon as you make it into the ammonium chloride, you change it into an acid. So the pH would be an acid of the ammonium. So that was good. My brain finally came back. So it would have a lower pH. And so a test with litmus paper would actually be the better indicator than boiling point. I don't know if we're going to do boiling point with your unknowns. It probably depends on my tolerance to want to do that. Because it's not the easiest test to do. I will. Is there any questions? Okay, I'm going to stop recording and